Good afternoon, students. How are you today?
Good, sir. And you?
Oh, not so bad. Got myself a tea full of honey and sugar. It's gonna keep my voice from cracking. I know I said we start at 2 p.m., so I'm gonna hold truth to that. I'm just gonna go help myself to some water, and then we'll do tutorial number dos. So I'll just be right back. All right. Hello again. You're live. So, hope you all had a good week so far. And I got the chance to look at the lecture recordings. Thankfully, nothing too bad this week, eh? Not too many recordings. So you're starting to see a lot of the stuff we learned this chapter compounds on the basics produced in the last one. And that's kind of going to be the rule of thumb for the next few chapters. We're just going to be building on the mechanics of waves based on what we already know about them. Anyways, a few orders of operation. I think you've all seen the first assignment up. The lab number 1 will take place online on Friday. There's 2 sections, so some of you will be doing it earlier than the other half later that day. Sent you a link on Omnibox so you can access the lab. Hopefully you've talked to Eli and got a hold of the lab kits by now. If not, you can do so before Friday. The official midterm has been decided for March, which is March 10th at 9 a.m. taking place at the college. In doing so, we will take all measurements so that everyone is safe. The midterm will be, you have like officially, we're in the room from 9 to 11. So I'm going to ensure that it's not the kind of midterm where like you're rushing to get it done in 2 hours. I don't want that. I don't want to test how fast you can answer physics questions, because I've been to grad school. They don't test you on speed. They actually expect you to spend a long time working out problems and their solutions. So to me, to already put you in like an environment where you're getting assessed because of the test, and also demand that you do things with a strict time limit, is a little bit silly and not representative of the real world. So I'm gonna make things so that it doesn't actually take 2 hours. Just do every question once and break a sweat. I just want to make it so it's a nice smooth sail. That said, though, I do want to bring up the fact that, well, one does the assignments, if it's tempting to highlight the assignment question and like paste it on Google and probably find some like Chegg or Yahoo Answers or something that kind of has the question worked out. Well, I understand the sort of situation one might be in where one just wants to peek at the solution. I do want to encourage everyone to try their best at, getting the questions through on their own, and sort of, if you get stuck, of course, you can always send me an email or check out the office hours, talk to the people at the, there's a tutoring center at the college now, or even, talk amongst your fellow classmates. That said, obviously, even if you are working together with a classmate, if your two homeworks look identical, then only one person is going to get the grade for that, right? Because if like two homeworks look the same, then it looks like just one person's job. But yeah, still, work is always should be your own at the end of the day. And beyond that, just gonna go ahead and get to our tutorial. And we're like an hour and a half today, so we can actually tackle a lot of questions. Fantastic. I don't have much else to add to the review, since we only really covered 2 more topics. Okay.
Sure.
Yes.
Would it be possible to post the last class's recording? I wasn't able to stay the whole class, so I kind of missed the ending.
Oh, last class. Yes. Thank you for reminding me to do that. It's not automatic because it gets saved to my cloud, not the servers, like not the closest class. So if you never see it, just send me a reminder and I'll put it up.
Okay. Thank you.
Okay. So how do I? There we go. There we go. It's almost a puzzle to figure out how to put it full screen. Okay, so we already talked about the sound waves, wave functions. You want to talk about them, you can talk about the position of any particle in the medium, whether that's a gas chamber, so kind of like a one-dimensional tube where waves just kind of go left to right, or even like a kind of like a ripple of sound, a sound source on ground just kind of emitting these ripples that are actually kind of like, you can't see them, but they're actually like spherical bubbles. Those wavefronts are just bubbles that keep coming out of the source. And since most of the time we're talking about sound being transmitted through air or through gases, we're sometimes interested in talking about how the oscillations in the medium essentially cause pressure variations throughout the gas, throughout the air. So rather than having a wave function that talks about the positions of air particles as they are disturbed by the wave, we can talk about it in terms of the pressure variation. And rather than having an amplitude of oscillations, you have basically this max displacement or this max pressure variation, which is, again, the same notion as amplitude in a transverse wave. So that depends on how much energy is being outputted by the sound system. Pressure variation, of course, is related to how much the gas molecules are oscillating, plus how fast the wave moves times what dense the gas is and the frequency. Makes sense, right? Because a faster gas is kind of moving back and forth like a accordion, or kind of changing pressure much quicker, right? Going from like high pressure, low pressure very quickly. So that's why there's this direct proportion between speed and pressure change. We've seen that already. And the wave function, whether you're talking about pressure or displacement, it's sine or cos. So right, max displacement occurs at points where particles then have moved quite far from that position. So it leaves a point of low pressure. And then there's these regions called the compression point, where the particles in the middle actually haven't really displaced all that much, but they are getting sandwiched by the particles on both sides. And then over here's a little GIF of the particle moving. And then we talked about the velocity for waves depends on how stiff the particles are over their density, so v over rho square rooted. And in air, the sound waves get faster the hotter air is. And waves move faster in solids and liquids than in air. And also you can talk about the intensity of a wave based on how much energy is coming out or pressure variations over some area. The intensity is in some ways involved in how we perceive sound, but there's not like a direct relationship between like loudness and intensity. There's a complex relationship between how loud, how intense the sound is, and its frequency, and whether or not we'll be able to hear it. And there's a huge range of intensities we can hear. So we compress that range into a log scale using the sound level formula, and we can measure intensities in decibels. So again, intensity drops off the farther away you are from the source. And we found out that there is a particular range of frequencies and intensities for which the human ear can perceive sound. As we go towards the lower threshold of hearing, there's only a certain range of frequencies that we're sensitive to. But as intensity increases, in this case, sound level, same thing, then there's a bigger range of frequencies that we can hear. But if the sound level is a little bit too high, then we start experiencing pain. And finally, we talked about the Doppler effect, which is the perceived shift in pitch when objects move towards or away from us. Basically, when a car is coming towards you on the road, it sounds like the car, like the engine sound, has like a higher pitch, and then as it drives off, it kind of like drops off, and that's because as it comes towards you, the sound waves are approaching you at a faster rate, so you hear a higher frequency, and your ears understand that as a higher pitch, and then as a car moves away from you, the waves are kind of farther apart. Each consecutive wave coming out of the car has to catch up to the previous one. So that ends up meaning that you have longer waves coming towards you, meaning that they have a shorter frequency, sorry, a slower frequency. Because right, like if wavelength is big, frequency is small, and a small frequency means that the amount of time that waves take to arrive is longer, so there's less waves that arrive per unit time. Anyways, the Doppler formula here just kind of just consolidates everything that can happen. The top part of the formula accounts for the observer moving, and the bottom part accounts for the sound source. And it measures basically everything in parentheses, measures the shift from emitted frequency to what's going to be observed or detected by the person hearing the sound. So the first term of both the numerator and denominator is the speed of the sound. Then this term is for the speed of the observer. This term is for the speed of the source. If the observer is moving towards the source, you use the positive sign. If you're moving away, you'll use the negative sign. But it's the other way around with the denominator, because if the source is moving towards you, that increases the frequency, so there's going to be a negative sign here. But if the source is moving away from you, you'll pick the plus sign here, which is overall going to make f prime smaller. And we saw that the Doppler effect can happen in all waves, including the electromagnetic waves, which is why stars that are moving away from us appear red, and moving towards us appear blue. Okay. Let's put our knowledge of this to the test. Why? I swear, Zoom's giving me a hard time using basic slides. There we go. Okay, so Garfield and Ollie are friends, and Garfield's just standing around being a cool cat, and Odie here just barking. So that means that Odie's essentially using his voice box to send sound waves towards Garfield. Now, the frequency of sound waves that Garfield detects, is it higher, lower, or equal to than what's coming out of Ollie's mouth? What do we think?
Lower?
Okay. Why is it lower?
Because the dog would hear it louder than Garfield would.
Right. And what about the frequency, though? What about the frequency of the waves? Would it be the same or lower?
Lower at Garfield.
Okay. So remember that, well, yeah, intensity does drop as you move further away from dog. The frequency would, in this case, remain the same because frequency, right, is part of the is a function of the speed of sound in air, and in this case, both Garfield and Aldi are standing still. So everywhere between them, right, the air is the same. So the sound waves move at the same rate, and therefore, if they're moving at the same speed, then the frequency right over here, out of Aldi's mouth, should be the same frequency of sound that reaches Garfield's ears. It's true that, yeah, like the intensity, the waves do spread out, so the intensity per unit area does decrease, but the frequency in this case will remain the same. So if we look at the Doppler formula for finding the Doppler shift between what Garfield hears and what's actually coming out of Ollie's mouth, this term here will be the speed of sound in air. So with this one actually, but this term here again accounts for the speed of the observer, which is Garfield, who's not moving, and the source is not moving either. And so what you're left with is, right, you have like a 0 here and a 0 there. So you have the speed of sound over the speed of sound, which would just give you, 1. So you have a factor of 1 times f, which in other words means that the detected frequency by Garfield is the same as the frequency coming out of Ollie's mouth. It's also worth pointing out, right, that we don't actually, like our ears are not frequency detectors so much that they interpret frequency as a pitch. And so when cars move towards you, you hear a higher pitch. When they move away from you, you hear a lower pitch. I wonder actually if I can do like a quick. I'm gonna show you like a. Oh, is this it? Hang on. Trying to find like a race car example. Ah, yes. Okay. I'm gonna show you a little screen share here of the Doppler effect in race cars as they move towards the camera crew and away from the camera crew. So I'm gonna do a share sound. Hopefully you can hear it. Okay.
Maybe not a bad place to be. Check here with Giafoni working him. Right.
And that's it, right? That's the sound you hear.
Check here with Giafoni working him.
So it sounds high pitched at first, and then it like alters off. That's the Doppler effect. So they're coming towards you, it's high, and then they drive off away from the camera, kind of drops off. That's what's happening, and that's only because the cars are moving. Okay. Now this. Okay, I thought so. Okay. YouTube kept playing the video. Okay. Now, so yeah, we agreed that in this case, Garfield, like what Garfield hears is the same that's coming out of Ollie's mouth. Now, what if Ollie's barking and walking towards Garfield? Will Garfield hear a higher pitch, a lower pitch, or the same?
Higher.
That's
We'll
right.
hear a higher because the frequency will be squished towards him.
Exactly. Yeah, because as he keeps moving, he keeps emitting sound waves closer and closer to Garfield. So it looks like even though they're being emitted at the same rate, the apparently what it looks like physically is that they're closer together. As such, they hit you faster and you perceive a higher pitch. And this is reflected in the formula because for the Doppler shift formula, there's no observer speed here, but just speed of sound. So we'll be using a plus sign or a negative sign here at the bottom of this formula for the speed for Audi. Is it a plus or a minus?
Minus.
Yep. And that makes sense, right? That's just going to make the denominator smaller, leading to a upward shift. Okay, nice. Now Garfield decided to buy some cool shoes, and they're both kind of running away from each other. So we actually don't know for sure what the overall shift is going to be. It depends on who's faster. If Garfield moves faster than Ollie, then he'll be able to kind of like the waves
One
will
is
catch up to
minus,
them.
one is positive.
What's that? Sorry, I didn't quite catch what you said. I thought someone say something about something being positive.
So the top part would be negative and the bottom part would be positive.
Yeah, exactly. Garfield's trying to run away, so that's going to decrease the pitch, but Ollie's moving towards him, so it'll increase. And the overall effect depends on which one of them is faster. Nice. All right. So again, the one on top is for reference. This one's nothing's happening, but yeah, if Ollie now moves away from Garfield, then there's no observer term, but then this will decrease what Garfield hears since each wave's gonna farther apart because they're being produced farther away from Garfield each second. And the other situation is Garfield and Ollie are walking towards each other. And this is the best case because for sure, if they're walking towards each other, the frequency is going to, the pitch is going to increase. In this case, the pitch decreases if Ollie's walking away from Garfield. So it's going to be, this would get for writing with my right hand. And yeah, the sign here, if they're walking towards each other, is a positive sign for Garfield and a negative sign for Ollie. So there we go. That's a general idea. Oh yeah, last thing, super cool thing. If you move fast enough, you can actually outrun your own ripples. And what that does is it creates this sort of wavefront, like this conical wavefront that has all these ripples like amounting together, hitting at the same time. So this is like a lot of energy in this front, in this shock wave. And this only really happens if you can outrun sound. So the things that can outrun sound then are, like bullets or even the crack of a whip or fighter jets. And when they do that, when they really fly off faster than sound, then this shockwave happens. And so all this sound kind of like hits you all at once rather than, having like waves of sound hitting you. It's like a huge wave made up of like overlapping ripples hitting you. And that's going to hurt. That's what's called a sonic boom. It's when the shockwave just like hits everything in surroundings. I have like a short video on it, which I think does a more justice than a bunch of slides on them. So I'm just gonna put that on.
I have a question.
Yeah, what's up?
Later in the slides, are you going to explain the match number and how it was from colder to hotter. And one of the questions you were answering it, but I didn't really understand it.
In the short quiz, yeah. So I guess I'll have to go with it now. I actually have a short little blurb here. So first of all, this relationship on top here. This talks about the relationship between how wide the shockwave is and how the speed of sound compares to the speed of the source. So Vs is not the speed of sound, it's the speed of whatever is flying in the air. And basically, if you remember that sine theta from say 0 to like 90 degrees, it increases with theta, right? So as the angle goes from 0 to 90, sine theta gets bigger. So this is basically saying that the angle of the shock wave, if the speed of your plane is really, really small, then your shock wave is going to have a pretty big angle. It's going to be a pretty wide shock wave. But when you're flying really, really many, many times faster than the speed of sound, say you're flying 10 times faster than the speed of sound. So this fraction becomes 1/10 because you're flying 10 times faster. So you have sine theta is equal to 1/10. So the angle for that is like an angle of like 1 degree. So that's saying that as you fly faster and faster and faster, the shock wave becomes much more narrower. And that's dangerous because effectively you have like a very narrow shock wave, then you have a much more concentrated sound waves over a smaller area. So again, the angle of the shock wave essentially depends on how much faster sound is compared to the flying object. Match speed is actually just the reciprocal of that ratio. Match speed is how many times you are flying faster than sound. So it's literally just the ratio of your speed to the speed of sound. So when we say, oh, that's this jet plane I got, yeah, it can go up to a Mach 5. It's saying that it can fly 5 times faster than sound. So that will be about 1.5 kilometers per second. So the way you measure that is take the speed of your plane, divided by the speed of sound, that'll give you your Mach number. By the way, remember the speed of sound moves like 1/3 of a kilometer, or in other words, every 3 seconds, sound has moved a kilometer. That is pretty dang fast. It took a while for us to actually design planes that can move faster than that, and even then, they can't be that big. So, where was I? Yeah, have a little. Wait, am I sharing sound? Yes, I am. Optimize for video clip. Oh, I haven't seen this option before. Okay, is everyone seeing? Can anyone see the TED Talk on YouTube? Is this showing?
Yeah.
Okay. Put on captions.
Humans have been fascinated with speed for ages. The history of human progress is one of ever-increasing velocity, and one of the most important achievements in this historical race was the breaking of the sound barrier. Not long after the first successful airplane flights, pilots were eager to push their planes to go faster and faster. But as they did so, increased turbulence and large forces on the plane prevented them from accelerating further. Some tried to circumvent the problem through risky dives, often with tragic results. Finally, in 1947, design improvements such as a movable horizontal stabilizer, the all-moving tail, allowed an American military pilot named Chuck Yeager to fly the Bell X-1 aircraft at 1,127 kilometers per hour, becoming the first person to break the sound barrier and travel faster than the speed of sound. The Bell X-1 was the first of many supersonic aircraft to follow, with later designs reaching speeds over Mach 3. Aircraft traveling at supersonic speed create a shockwave with a thunder-like noise known as a sonic boom. which can cause distress to people and animals below, or even damage buildings. For this reason, scientists around the world have been looking at sonic booms, trying to predict their path in the atmosphere, where they will land, and how loud they will be. To better understand how scientists study sonic booms, let's start with some basics of sound. Imagine throwing a small stone in a still pond. What do you see? The stone causes waves to travel in the water at the same speed in every direction. These circles that keep growing in radius are called wave fronts. Similarly, even though we cannot see it, a stationary sound source, like a home stereo, creates sound waves traveling outward. The speed of the waves depends on factors like the altitude and temperature of the air they move through. At sea level, sound travels at about 1,225 kilometers per hour. But instead of circles on a two-dimensional surface, the wave fronts are now concentric spheres, with the sound traveling along rays perpendicular to these waves. Now imagine a moving sound source, such as a train whistle. As the source keeps moving in a certain direction, the successive waves in front of it will become bunched closer together. This greater wave frequency is the cause of the famous Doppler effect, where approaching objects sound higher pitched. But as long as the source is moving slower than the sound waves themselves, they will remain nested within each other. It's when an object goes supersonic, moving faster than the sound it makes, that the picture changes dramatically. As it overtakes sound waves it has emitted while generating new ones from its current position, the waves are forced together, forming a Mach cone. No sound is heard as it approaches an observer because the object is traveling faster than the sound it produces. Only after the object has passed will the observer hear the sonic boom. Where the Mach cone meets the ground, it forms a hyperbola, leaving a trail known as the boom carpet as it travels forward. This makes it possible to determine the area affected by a sonic boom. What about figuring out how strong a sonic boom will be? This involves solving the famous Navier-Stokes equations to find the variation of pressure in the air due to the supersonic aircraft flying through it. This results in the pressure signature known as the N wave. What does this shape mean? Well, the sonic boom occurs when there is a sudden change in pressure, and the N wave involves two booms, one for the initial pressure rise at the aircraft's nose, and another for when the tail passes and the pressure suddenly returns to normal. This causes a double boom, but it is usually heard as a single boom by human ears. In practice, computer models using these principles can often predict the location and intensity of sonic booms for given atmospheric conditions and flight trajectories, and there is ongoing research to mitigate their effects. In the meantime, supersonic flight over land remains prohibited. So are sonic booms a recent creation? Not exactly. While we try to find ways to silence them, a few other animals have been using sonic booms to their advantage. The gigantic Diplodocus may have been capable of cracking its tail faster than sound, at over 1,200 kilometers per hour, possibly to deter predators. Some types of shrimp can also create a similar shock wave underwater, stunning or even killing prey at a distance with just a snap of their oversized claw. So while we humans have made great progress in our relentless pursuit of speed, it turns out that nature was there first.
Pretty cool. Where did I? There it is. Oh, by the way, it would be lovely if the PowerPoint actually loaded. It's kind of quit its job after the sonic boom thing. Hang on one second. There we are. Okay. Oh, something cool. Something cool about this sonic boom business is that, like, you saw how, like, yeah, when a plane flies really fast, there's like this sudden pressure change, that's kind of like slower than the plane. So the plane kind of moves by really fast, and behind it, it leaves this like quick vacuum that gets filled in really quick. And in that short sort of filling in of that vacuum creates like a big change in pressure, creates like a huge wave. Interestingly enough, that can also happen with electromagnetic waves. And I'll talk about this in a few chapters, but if you have a really fast like cosmic ray moving through the atmosphere, they can actually very quickly create this like huge dipole in the air, and they're moving so fast that they leave this huge dipole behind. So all the dipole particles that got left behind all of a sudden switch back to their normal state. This switchback that happens creates a huge burst of light. So it's kind of like a sonic boom, but it's like a light sonic boom. And what's even cooler about that is that if you can actually detect that light, you can learn about the cosmic ray that's responsible for it in the first place. Okay, yeah, so I have some formative questions we can do for the rest of the day. This first one's for you guys, sorry, for all of you. And you have a siren moving east, you know its frequency of the bell, and you have a cyclist moving west who is standing in front of the ambulance. So should have probably I guess the situation here is actually flipped, but for all intents and purposes, the cyclist is moving west. So probably have the cyclist in here. Here we have the cyclist, here we have the ambulance. And the question is, what frequency is heard by the cyclist? So I'll give you 2 minutes to try it out. Yes. Okay. So thinking about this question, if the ambulance is moving in the opposite direction that the cyclist is moving, do we expect the pitch to decrease or increase?
Increase.
Yeah, exactly. It's like it's like when you go swimming and like you wanna you wanna catch some waves, you wanna surf, you swim towards the waves so they hit you faster. So we can expect exactly that. I hate when Zoom keeps doing that weird scripting thing. We can expect the pitch to increase. Originally, we have about 500 hertz of frequency, so our answer should be bigger than that. So it's not the very. Okay, well, the answer lies in just using the Doppler formula. So you can probably narrow it down to either 340 or 350 for the speed of sound. And if we say the top part is for the source, which is the cyclist, or for the observer, the cyclist, and yeah, the bottom part is the ambulance times the original frequency. This is doing the lecture. Forget to get the F.
Sir,
Yes.
the number is supposed to be 345 instead of 340.
Okay. I kind of rounded down. I chose to round down the speed of sound by like numbers of 10. So 343 would be like 340. But yeah, it's also true that the problem does give you the actual velocity of sound. So thank you. That needs to be yeah, we should respect that. And I have a ambulance speed of 35. So this, again, this is the shift factor. We're going to take that times the original frequency. And this should be about this answer A. Okay. Right, there we go. Okay. So again, I'll give you 2 minutes for this one. By the way, it's the same ambulance and same speed. But now you are the observer and you're at rest. Okay. So I'll start talking about it, but if the frequency is coming towards you, it's going to be bigger than 500, and then the other way around if it's less than. So F1 will probably be about It's about what is it? 345. Now in F2, it's moving away from you, so the frequency should drop. And I believe you should be around. Not that if you're not moving anywhere near the speed of sound, the shift is not that dramatic. So if it's moving away from you, the shift is only like a factor of like 1.1. So that's like an increase of 50 hertz really of pitch of frequency. In the case of this, where it drops a little bit, it's something somewhere around 450 hertz. So if you're looking for the difference between them, hertz. So 100 hertz of difference is not too much. If you look at the notes on a guitar, that's like comparable to tuning the guitar up or down a little bit. Remember, the human ear can hear like a range from like anywhere between 20 and 20,000 hertz of frequency. Just to give you kind of like an idea for the scale of things. Okay. Let's go on to the next question. Eh? Oh, nice. Okay, yeah. So we got a fighter jet here, and it's flying at Mach 1.67. And what should be the angle of its shock wave? Well, I'll do this one, but basically, right, the Mach. Yeah, Helium Zoom keeps doing that weird scribbling thing. I'm just gonna use the PowerPoint marker instead. Nice. Okay. So I just learned today that it's Mach, not match. I kept saying match my whole life. That's equal to how much times faster you're flying in sound. So this is your jet over the speed of sound. But the relationship between the angle of the shock wave and your plane is it's like a sine theta relationship. So this is actually equal to 1 over your Mach speed. So sine theta will be equal to 1 over 1.67. And to give you an idea, 1 over 1.67, that's somewhere around 0.6, right? So at this point, you can take the arc sine to get what the angle of the what the angle should be for the shock wave, and by taking the arc sine, you should get around 36.8 degrees. So it's a fairly narrow shock wave. Anyways, now you've seen me do it. For the next one, I'll have you do it. If Zoom can let me do things. Okay, we have another fighter jet. This one's moving at Mach 2. And the question is, what should be the angle of its shock wave? So I'll let you figure it out. Just remember, right, the faster you go, the narrower the shock wave. maybe I'll start like slowly writing it out. Remember, it's always going to be this is well, looks like we basically have sine theta. By the way, you should not even like have to use your calculator for this, ideally, because sine of theta being equal to 1/2, that's a very common angle. That's 30 degrees. And would be, as a matter of fact, right, from like 0 to 90, you should probably know that sine of 30, right, that's going to give you 1/2. What is it? Sine of 45, that gives you about 0.707. And sine of 60 gives you around, I think, 0.868. And of course, this maximum sine of 90, which is 1. Although you're at it, cos is the other way around. Cos of 0 is 1, and then it decreases towards 90. Funnily enough, cos and sine have the same value at an angle of 45 degrees, which makes sense because at 45 degrees, the x and y dimensions of the unit circle triangle are the same. And obviously cos then reaches and minimum at 90 degrees. So worth knowing the values of sine and cos for these angles. All right. Next question. Calculate displacement amplitude for a 20 kilohertz sound wave inside helium. Okay, we need to know displacement amplitude. I know displacement amplitude is a mouthful, but it's just, right, it's just delta to max change. So this is the max change in pressure. So this also counts as an amplitude. So it's kind of like the pressure variance or pressure amplitude. Displacement amplitude is S max. So remember that there's a relationship between the two, pressure amplitude and displacement amplitude. So if you know one, you can find the other. In fact, big enough hint. I'll let you calculate that, see what you get.
Sir,
Yep.
the screen went dark.
Oh, weird. Can you see it now?
Yeah.
Very nice. Okay. Let me. Oh, interesting. So it looks like a possible. Okay, I see. Let me see. So slowly, I'll slowly start taking a go at it myself. You know pretty much everything. Okay, so yeah, just plugging into what you know. I'm gonna just do some rounding here for the speed. 2 pi, it's about 6 times 28. So that's 120. 0, 0, 0. You should get for the answer should be around 3.7 times 10 to the 10 meters, which is option B. So again, it's just gonna, you know, the relationship between displacement and pressure. So okay, on to the next one.
You're gonna post this tutorial, right?
Yep, I'll put up the recording, and also you can have you have the slides put up as well on Omnivox.
Okay, hang on one sec. So does this go with the videos that you post, like on the YouTube link, or are you gonna put it with like the other thing, the thing
Oh.
on Omnivox?
Yeah, yeah, so I'll yeah, the tutorials will all be on YouTube along with the regular lecture recordings.
Okay, because you put the February 3rd one on the YouTube list.
Yes.
Like that was a tutorial we did together though, wasn't it?
Yeah. So the tutorials will also be online, even though we did them together. They'll be on YouTube for if you want to do them again, or
Okay.
do something
Perfect.
one more time.
Thank you.
No worries. But yeah, do sometimes remind me of the tutorials because they don't get recorded automatically to like the college's cloud. So just a manual thing, just an extra step. Okay. You are now looking for the intensity of a wave in a tube of helium, and you're given pressure, amplitude, you're given speed and the density. So you need to think of the relationship between intensity and amplitude for pressure, and we'll let's just give you the hint here. See if you can find the right intensity. Okay, so, well, we know P max. We know density here, and we know speed. So it shouldn't be too hard to find intensity. Okay, well, if you don't want to use a calculator, note that 2 times 0.18, that's like about like 0.09. And then you have 8 squared divided by 9. So 8 squared is about 64. And divided by 0.9 will give you about 1.8. But if you do plug this all in, which you should, just to make sure, you should get 1.8 times 10 to the negative 7 watts per meter squared. So not too bad. Why? Once I'm gonna like fight with Zoom. Okay. All right. So JetBlink has a sound level of 150 decibels. What's the intensity? So again, I'll let you try out this question. What's sound level anyways? Well, we know that it's has a relationship with intensity, right? Based on a threshold, which is 10 to the negative 12. And we're told what the sound level is, so just need to find intensity. I'll give you like a minute to see if you can get it. Excuse me. Get more water. Okay. We know everything except the intensity. We're trying to find that. We can actually do some quick algebra to write intensity in terms of sound level. In this case, the sound level is 150 decibels, but even so, here's what I'm gonna do. I'm gonna isolate for intensity here. I'm gonna take this 10, bring it to the other side. Also, I have a logarithmic function to get rid of, so I can just take the power of 10 of both sides.
Sir, I have a question.
Yeah.
So is the 150 decibels equal to 10 log intensity over the initial intensity.
Yep.
rise. So wait, you make the 150 equal to that equation?
Yeah, because the equation gives you decibels, right? So that's how you get sound level. So yeah, one matches the other.
Okay, because I don't understand like what the B is there. It's not decibels. Like you have it equal to.
Oh, this is the Veda, right? So sound level can be written, the shorthand Greek letter for sound level is beta. Not to be confused with the unit decibel, which uses the English letter dB.
Okay, I just don't understand where decibels comes into this. So like it's not anywhere in the equation. The 150, what happened to that?
Oh, you haven't plugged it in yet.
Okay.
Yeah, I left my term for the sound level on the left hand side. I left it as beta for now.
Okay.
Had I wanted to, you're right though. Had I wanted to, I could have.
I would have just plugged it in right away because
Yeah.
I just think that's easier.
Just could have plugged it in.
Okay.
Yeah, we can just do that. Whichever way you're more comfortable with, you can do it step by step. Just kind of showing like a general idea to this, because it might not be the last time you have to find intensity given a sound level. So that's why I'm keeping the sound level as is. Okay, and then effectively, you have that intensity then is equal to the threshold times 10 to the power of Veda divided by 10. And then, right, this is always going to be applicable to find any intensity given any value of Veda. In our case, we have Veda of 150 decibels, so we can plug that in. And again, you can just probably, I think, if I were a student, I would have probably like plugged in Beta right away at the start. I just can do it piece by piece. But this is kind of showing you the whole idea. So we have the threshold is 10 to the negative 12 times 10. Beta is 150, but we're going to divide it by 10, so that's just 15, right? So should give you 10 to the 3, which is 10,000, which you see. So you probably noticed by now how we do a lot of algebra in physics. If you ever have a little time to practice, being comfortable with algebra, that will probably save you some time in future physics classes, since you'll be able to kind of process the math at a good pace. And not necessarily, again, like the number one skill to sharpen during a physics class, but it's still overall a skill that is helpful in all math and physics classes.
So wouldn't it be D, not E?
Sorry?
Wouldn't it be D and not E?
It would be D and not E. Thank you.
Thank you.
Please, like call me out and stuff like this when you see it. Awesome. Yeah, 1000. All right. What do we have next? All right. How fast is the Concorde moving if it reaches Mach 1.5? So you know what? This one I'll just say it out loud, right? Mach, that should tell you right away how many times faster in sound you are. So the speed of sound is like 350. So it's like 1.5 times 350. What's 350 divided by 2? Approximately. Like 175, right? So 350 plus a half, right? Plus half of 350, that's somewhere around 500. So we don't even have to plug anything else, right? We could have plugged in, right, that Mach is equal to the ratio of the speeds times that the speed of sound. So, we could plug in 1.5 times 344, But we do know, right, from some simple mental math that it's about 500, so we circle B. So again, now, that's why it's always, especially for multiple choice, it's good to have like a sort of be warmed up in algebra, since that way you can kind of glance at the question quickly and get a feeling of what the number should be, look at the answers available, and find the one that's closest to the number. Okay. You hear the horn of a car approaching you. The frequency you hear is larger, of course. And the question is why? So which of these 5 options explains why? Give you a few seconds to guess, but given what we discussed, I think the answer is in sight. So the car horn's approaching you. So the wording here is a bit, I think, convoluted. A and B talk about the distance the car travels in one period. That's just saying that the car is constantly moving. So in a single period, a new crest gets emitted, and as such, it's going to be closer together to the previous crest because the car has moved, or at least it's going to be closer together on one side. So, and then if you look at part A, wave crests are, well, in your case, in your side of the road, wave crests are actually closer together. So it's not part A, it's obviously B. The remaining options are false. So the car's not going at supersonic speed. And part E is not true. The speeding car doesn't actually affect the sound waves it's producing. Okay, this question, you're like, bear with me for the context of this question. You're like playing with like a toy whistle. It's one of those instruments that you just kind of, it's like a flute, but there's like a sliding part of it that as you slide it up and down, it changes the tone of the pitch, the flute. There's kind of like a whistle that can be modulated. Your friend's running towards you, but you want her to hear the same frequency of the note you're actually playing on your whistle. So what can you do? So let you think about that. Your friend's running towards you and you're playing on the slide whistle. Who hasn't ever, has this ever happened to you? Who hasn't been in this situation at some point in their childhood? To be fair, they had there's so many examples to be made with sound, and eventually some of them are a bit luckier than others. Okay, if your friend's running towards you and you're playing an instrument, are they going to hear a higher, a lower, or an equal pitch to what's coming out of your slide whistle?
Higher.
Yeah, they're hitting the waves faster. So what you can do is you can make it so the relative motion between you and your friend is 0 by moving away from her or moving away from them. And so just run away in the same speed, because that way, right, if your friend here is moving towards you some speed and you're moving towards them with some other speed, you know the formula. If the speeds are the same but in the opposite direction, then the shift, you'd have minus b o and then v minus bs. But if the speed of the observer and the source are the same, then this just cancel out and you just get like a factor of 1. So the frequency will be the same. if you're moving away from each other. Sorry, if one's moving towards you and you're moving away from them at the same speed, they are coming towards you. So, okay, well, that's it. What else? You want to decrease the intensity of sound from a speaker system by a factor of 36. What can you do? So, all questions talk about changing amplitude and distance. So think about what the relationship is between intensity and distance and amplitude. And remember that for sound, the notion of amplitude is represented by either pressure variations or displacement of particles. But basically, the idea of amplitude is pressure variations or displacement variations. So then what's the relationship between intensity and distance? And also, what are we trying to do? Well, our goal is to take our intensity and have it reduced by a factor of 36. So I'll give you some time to think about. I'll keep drawing hints. So hint number 1. Hint number 2.
Sir,
Yes.
will there be a multiple choice section in the like midterms and stuff?
In the midterm, probably not. In the final, yes.
Okay, and
I have a question about if you're gonna put multiple choice. Are they gonna be like as difficult as something like this? Because I find this question is quite difficult. Like you need to know every like formula for intensity.
I would say that this type of question would probably be something that could end up, this could end up in a multiple choice section. I don't think all of them will be this level of difficulty, but I will expect you to, because you are going to have a formula sheet, right? So
Okay.
it's totally fair to expect to sort of work with the formulas and like look at the proportions. Again, this one's particularly challenging, so maybe 1 in 30 multiple choice will be this level, but this is
Okay.
still the general idea of what a multiple choice question can be like.
Okay. Thank you.
oh, sir, I have another question.
Yes.
Are we expected to come to school for physics class?
For the classroom?
Yep.
So the current policy is that so I decided that for the time being, I will not be holding classes in person at the college. So until further notice, all tutorials will take place online on Wednesdays and Fridays, as we have done before. if this is subject to change and courses or classes are offered at the college, attendance to those classes, like physically being in the classroom, would be optional, and you would still, of course, be fully allowed to simply attend the tutorials from home as you're doing so now. And if classes do happen in person, there would be a limit to about 17 students in the classroom at a time. But again, I am currently not providing in classroom sessions. So for the time being, all tutorials are still happening on Zoom. Okay. So this question is kind of tricky because you're asked to look at the proportions between two different terms. We usually look at one proportion at a time. The classic one, the most common one they like to ask you on is the inverse square relationship between power and distance. But also remember that the relationship between intensity and the pressure amplitude, which is a square relationship. So if you were to reduce amplitude, which is to say reduce delta P, that's also going to reduce intensity. If you reduce the amplitude by a factor of 2, you reduce intensity by a factor of 2 to the power of 2. So intensity drops by a factor of 4. If you also drop your distance by a, if your distance increases by a factor of, say, 3, then because of the inverse relationship, the inverse square relationship, the intensity drops by a factor of 3 squared, so a factor of 9. So if you do both these things, then intensity drops by a factor of 4 times 9, which is a factor of 1/36. Da-da-dum. So again, probably not every multiple choice will be at this level, but the general sort of ability to understand proportions and how two things can be modified to create an overall change in, say, intensity or something else, that is a skill that I would probably expect you to demonstrate at least once on an exam or a midterm. Da-da-dum. Okay, a bird's about to poop on you, and bear with me, it's an example. I guess the poop is making a sound, at some frequency. It's a C major poop. God, it's approaching you. It's about to hit you in the head. If that's happening, what about the sound? What can we say about the sound? What can we say with the frequency of the sound? So maybe like a few seconds to think about this one. Okay, so the answer to this question is, so there's a poop flowing towards you and it's making a sound. If it's moving towards you, it's going to sound louder. But here's the thing, though, it's actually accelerating due to gravity. So it's moving faster and faster as it falls towards your head, which means that the faster it moves, the faster the waves bunch together. So there's a constant increase in frequency as the poop falls towards your head. Okay, I did not make this example. It's from the textbook, and I just find it funny that there's a disclaimer on this one, which makes it seem like the exception and not the rule for all the examples in the book. Where it's like, okay, this is the example you should not try at home. This one's going to kill you. Everything else, if we don't warn you, then fair game. But this one, do not try it. Okay, so yeah, you're standing below something with a fixed frequency sound, but this one's falling at terminal velocity. So imagine the bird poops on your head again, but this is a terminal velocity poop, which means that it's a constant velocity. As it approaches you, what can we say about the sound in this case? So I'll tell you, the difference between the bird's poop is that the bird's poop moves faster and faster due to gravity. This one's speed is constant, so there's only like its pitch is shifted, but it stays shifted all the way through its trajectory to the top of your head. So it stays at the same frequency from beginning of fall to the moment it hits your head. So stays at the same frequency. I'll put a little star here, right at the same. It's already shifted. It just doesn't change because the speed is terminal. Okay. So is this clear, the difference between an accelerating object falling towards you and one that's terminal? How one will increase frequency and one will just stay the same? All right. Oh, this one's cool. Okay. This is not, again, probably not something to put on midterm, but this is just something to think about relationships between properties. You throw a stone into the surface of water. So here's a little stone here, and kind of creates ripple outwards. The amplitude of the wave falls off with distance r from the point S. What's the relationship between amplitude and distance? Well, again, amplitude kind of talks about the pressure, right? How the pressure changes, and the wavefronts, right, where the waves of water are accumulated. That's when you have the most, the biggest pressure amplitude. So the relationship between pressure amplitude and distance is not quite obvious until you remember that the intensity of any wavefront is equal to the square of the max amplitude squared over the area of the wavefront. So for a spherical, right, when the wavefront was like a sound sphere, we had 4 pi r squared. But now we have just ripples on the surface of water. So the area of a ripple isn't so much the area, actually. This is actually going to be like a linear, it's just a circle, right? And a circle has circumference 2 pi r. So for a wave on the surface of water, it's not like a surface intensity anymore. It's not watts per meter squared. It's now a linear intensity. And going to be the unit for that's going to be watts per meter. So that's going to be 2 pi r for the circumference of the whole wavefront, right? So this is one wavefront, right? And its area, its diameter is 2 pi r. And right, as the wavefront gets bigger and bigger, the intensity spreads out over the diameter. Okay, but why do we care about this? Because we're looking for the relationship between amplitude and r. So, oh my God, I'm sorry. Fudgesicles. This formula here is not for P max, it's for the average power in the, this formula here is for the average power. Where am I? It's for the average power. But it's true though that it is related to the term here at the bottom is actually the diameter of the circle of the wavefront. So this formula will look like this. Okay. But it's also true, right, that intensity is related to the amplitude by this formula. 2 rho v. So we can then make this, we can take this 2 and make them equal to one another. So you have that the power is equal to 2 pi r. That's equal to the amplitude squared to rho v. And we're trying to find the relationship between amplitude and distance r from the impact point. So just kind of solve for the, if you solve for the pressure variation for delta P, what you get is the, you basically get a square root term for the whole power times density times speed. There's 2 here that cancels out. There's a rho and there's r. So basically, to get the amplitude, you just take a square root of everything. R is in the denominator, so there's a square root relationship between between the distance from the rock and the amplitude of the wave. And this is not something we'd expect you to do for a test, but maybe, you know, just sort of have an idea of how, with some algebraic manipulation, you're able to obtain any proportion between any measurement and the units in the, that anything that has to do with the same wave, you can manipulate to get the measurements. Anyways, we're gonna get kicked out in 1 minute. So unfortunately, that's all for today. If you have any questions, just let me know or send me an email. There's also office hours Mondays at 7. Good luck on the assignment, and we'll see you next Wednesday. Also, the lab is effectively on February 19th. It'll be online, so hopefully you have your lab kits and you'll join us then, where we'll be making pendulums and swinging them around. All right, see you next time. You're welcome. Yeah, very
Sir,
welcome.
do we have to learn the formulas by heart?
The formulas, you're gonna have access to a formula sheet during evaluations.
Thank you.
No worries. Yeah, I'm not gonna quiz you memorizing formulas. That's, again, that's not really what's the, but the competency, right? The competencies of this course are not about memorization, they're about conceptual understanding more than anything else. Also, I want to be fair, right? Like if you just suddenly ask me, hey, Mr. Chernitsky, what's formula in chapter 17?